Well, now let's take a look at example number 1 on the next page, which is going to ask us to evaluate each of the following different hyperbolic trig functions at different values. And if I know the formulas that we had established back in the previous video and on the previous page, this should be super easy to do. Let's take a look here quickly at hyperbolic sine of 0. So if I was to go ahead and attempt to evaluate this, I can see that obviously I would just plug in 0 for every instance of x. And I'll notice here that I really just have e to the 0 in the numerator occurring twice. E to the 0 is 1. And so I get 1 minus 1 over 2. That's 0 over 2. That's 0. So the hyperbolic sine of 0 is 0. Very interestingly, the regular sine of 0 is also 0. So those graphs actually have that point in common. If I was to take a look here at the hyperbolic cosine of 1, not too difficult. I can say this is going to be e to the 1 plus e to the negative 1 over 2. Now, unfortunately, there's not really any easier way I might be able to express this. I mean, I could get rid of negative exponents and write this as e plus 1 over e. I could pull the divide by 2 out to the front as a 1/2, but there's not much else I can do to simplify this down. In fact, I'm going to go ahead and just leave my answer like this as opposed to rounding off to get a decimal. If I wanted to do something like the hyperbolic tangent of 2, no big deal. I'm just going to do my hyperbolic sine and put that in the numerator, and then I'll divide by my hyperbolic cosine in the denominator. So let's see, this would be e to the 2 minus e to the negative 2. Remember, sine subtract. E to the 2 plus e to the negative 2. And of course, when I multiply by the reciprocal, very obviously my 2's here are going to be eliminated. And so I'm really just going to be left with an e to the 2 minus e to the negative 2 over e to the 2 plus e to the negative 2. And again, there's no real good way I can go through and attempt to simplify this up. So I'm just going to go ahead and leave it as is. Now, a couple things to note here is that oftentimes when we're working with these sorts of values in specific problems, we might want to know what exactly or how far I should go in terms of my simplification. If I was working with something like hyperbolic sine of 0, I would definitely be able to see that since I simplify down to a final answer of just a really easy number, I'll tend to not leave things in this form and simplify it all the way down. However, if I'm going to get a really ugly or nasty value, it doesn't simplify out to be a pretty easy looking number, it's pretty customary to almost just leave this value in as your answer. So I would oftentimes tend to avoid writing 1/2 times this quantity as my value and just kind of leave my answer as hyperbolic cosine of 1. You'll notice then that I can see the same exact thing when I get here to hyperbolic tangent of 2. It's not that these answers are wrong, but only that we don't oftentimes have to go that far in terms of trying to simplify these values. We'll oftentimes just leave them in our answers written in the following way. So we'll see that it's still going to be important to know the formulas that we established on the previous page, because that's the only way I can know if I need to simplify. But oftentimes we'll leave things in this form if the numbers, again, don't simplify nicely. Now, another thing that we're going to need to know about these functions is what exactly their graphs might actually look like. Now, you can think about why this might actually be important. If you think back to some of the other ideas that we've covered so far in Chapter 2, say for instance, surface area. If I was going to take one of these curves and attempt to revolve it around an axis to get a 3D solid and I wanted the surface area of it, one of the conditions for surface area is I needed to make sure that my curve was non-negative on the given interval. So being able to see whether or not these curves are going to be non-negative can be very important. In addition to that, it might be useful to know whether or not I believe these curves are continuous curves. And we'll be able to see pictorially as well as from looking at their formulas how we might be able to make determinations about both of these facts. So let's see. If I was to go ahead and take a look at each of these individual pictures, I'll see here that with my hyperbolic sine, go ahead and reconstruct that, and my hyperbolic cosine, Let me just set up each of these here really quickly. And then my hyperbolic tangent. For each of these graphs, I'm going to have almost a very recognizable shape. So let's see. For my hyperbolic sine, I'm going to get a picture that actually looks something kind of like this. It's actually going to go right through the origin. We saw that up above, that 0, 0 was a point that was on this curve. My hyperbolic sine graph looks something like this. Now my hyperbolic cosine graph has a shape that's almost parabolic. It's not quite a parabola, but it's pretty close. Looks something like this. I'll notice here that this crosses over at a point of 1. And we'll be able to see that because you might notice that if I was to take hyperbolic cosine and plug in 0, I can see that I do indeed get back the value of 1. Notice because that would give me 1 plus 1, e to the 0, remember, is 1. So 1 plus 1 is 2, and 2 over 2 is going to be back returning a value of 1. My hyperbolic tangent graph looks something like this. It also goes through the origin. But on this graph, it's interesting because there are going to be some horizontal asymptotes on this picture. I'll go ahead and sketch in here in this red. These actually occur at the values of -1 and +1 on the picture. Now, I like to try to remember these graphs by other graphs that these are very, very similar to. So notice that down here, I'll be able to say that the hyperbolic sine of x looks like another sort of a function. Can you maybe even tell what sort of a, or what function my hyperbolic sine looks like? Well, you might be able to see that it kind of looks like x to the third, right? Like it's very similar in shape. It's not the same, but it is very similar. And so oftentimes, like if I can make this association, it helps me to remember the shape of this graph. I can do the same sort of thing when I come down here to the hyperbolic cosine. This one kind of looks like, well, yeah, it kind of looks like an x squared, but since it's been bumped up 1, I'll say it looks like x squared plus 1. Now this one over here is very interesting because there is a graph that you would have talked about in probably, well, definitely in a pre-calculus class where you talk about trig, but certainly in a Calc 1 class that looks very similar to this hyperbolic tangent. This graph here very much looks like the curve, the inverse tangent, right? Or arctangent graph, which had the same basic blue shape and also had horizontal asymptotes, but on this graph they occurred at -π/2 and +π/2. So knowing these pictures is very, very useful. Notice that my cosine is going to definitely be non-negative, whereas my sine and tangent graphs there are going to actually become negative on certain intervals. I can see though that all of these graphs appear to be continuous, which of course is actually no surprise because if I go back to see how they're defined, they are actually just a continuous function plus or minus a continuous function divided by 2, and then maybe I'm just dividing those continuous functions. So these guys here are definitely all going to be nice continuous graphs on their domain. In the next video, we'll take a look at some interesting identities that can be formed with these new hyperbolic trig functions.